Assalamu alaikum everyone. Welcome to the 14th lecture of our numerical methods course. And the topic for today is Euler's method for solving ordinary differential equations. Okay. So the plan for today is to basically recall the whole concept of ODEs that you guys have already learned in your first year calculus course. We'll try to recapitulate the idea a bit, and then we'll try to understand the idea behind the Euler's method, and we'll try to derive it using two approaches. We'll try to derive the formula, and then we'll see how the error accumulates for the Euler's method using the Taylor series. And then lastly, we'll see an application of the Euler's method, an application where we use the Euler's method to solve definite integrals, okay, or finding the area under the curve between a lower bound and an upper bound within a range, okay, within an interval. Okay, so what's the Euler method? So this is a method that was jointly invented by Euler and Cauchy. So this is also known as the Euler-Cauchy method. So it's a numerical technique to approximate the solution to a first-order ordinary differential equation. Okay, or in short, we call it ODE, right? So if you guys can recall, let's go back to our map paper and see what an ODE looks like. Okay. Okay, so let's say we have an ordinary differential equation that looks something like what 69 dy dx plus let's say 420y equals say 911 e to the power minus x. Okay, this is a random first order ordinary differential equation. So what we can do is we can solve it analytically, right? So I won't go into the nitty-gritty details about the analytical approach because that's beyond the scope of this course. So if you guys can recall, what did you do? So in order to find out the value of y, the dependent variable y at a certain discrete point x, our target is to find this, right? Yx. So what did you do? You found the y particular part, if you guys remember, and then we figured out the y homogeneous part, the homogeneous part of the ODE. We called it y homogeneous, and we basically summed them together in order to find the actual value of the uh, dependent variable y at a particular point x, right? So we won't talk about the analytical approach in here. We'll simply see how we can apply the numerical approach or the Euler's method in order to find out an approximation of the solution to this first order ODE. Okay, so let's see how we can do that. So let's go back to the presentation. Okay, so the first course of action is, of course, to manipulate or symbolically manipulate your first order ODE in such a manner so that you can fit this template over here. Okay, you can cast your ODE into such a manner so that it fits this template. So you need two things in order to apply the Euler's method. Firstly, you need to manipulate your ODE in order to fit this template. Dy dx equals f of x comma y, where f of x comma y is a bivariate function, which means it has two variables. Okay, one independent variable x and another dependent variable y, and you need an initial condition. Okay, by the initial condition you can call it the initial value as well, which means for a particular initial point x naught, for the independent variable, of course, the x independent variable, we need to know the corresponding dependent variables value, okay, which is the y naught value. So you need to know the x naught and the y naught values initially as a starter. Okay, if you have these two things at your disposal, then you can apply the Euler's method. Okay, so the Euler's method is a very niche method because it can only be applied to solve or approximate the solution to the first order or ordinary differential equations. Okay, so in order to solve higher order differential equations, you need to perform some hacks and say improvements to the methods. Okay, the vanilla or the basic or the method in its most rudimentary form, you won't be able to solve higher order differential equations using it. Okay, so what we the first thing we'll do is, okay, so let's try out the example that we just saw in our bamboo paper and try to cast it to this template and see how it looks like. Okay, let's go back to our bamboo paper. Okay, so we already have our ordinary differential equation right here, and let's say we have an extra initial condition which is something like, okay, the value or the discrete value of the dependent variable y at a certain point 0 is, let's say, something like 5. Okay, so these two are given to us. Okay, so since if these two are given to us, what we can do is we can symbolically manipulate this. So let's say this becomes something like, so in order to cast it into the form of that template, we'll do what? We'll take this 420y and take it to the right side. Okay, so it should look something like what, 911 e to the power minus x minus 420y, right? And then what we can do is, okay, since our job is to get only dy dx at the left, so we'll do that, dy dx, and we'll take the factor or the leading coefficient 69 at the bottom of the right hand side. So ultimately we should get something like this, right? 911 e to the power minus x minus 420y divided by 69. Very nice. Okay, and our initial condition still persists, which is the value of y at the point x equals to 0 is 5. Okay, so after you have done this, after you have did, how do you say it? After you have defined the first order ordinary differential equation, or the ordinary differential equation in this manner, and you have the initial condition, you're good to go. Okay, you can now apply Euler's method to it and come up with an approximation of the solution at any other discrete point y. Okay, fine. So let's see the main idea or the algorithm behind the Euler's method and try to derive it. Let's go back to the presentation. Okay, and so before doing that, so notice that here at the right hand side we have two variables, right? X over here and y over here. So we can call it a bivariate function. The caveat is that x here is a independent variable and y here is a dependent variable. Okay, y changes with the change in value of x. Fine. So let's go back to our presentation and see what else we can do. Okay, so let's proceed. So here I have written down two more examples for you guys to practice. So these are pretty similar. The idea is that you have a first order ordinary differential equation and an initial condition, and your goal is to cast it into this form over here. Okay, so it's pretty simple mathematical side here. You can check them out if you want. Fine. So the idea for the let me switch to the laser pointer. Okay. The general goal behind the Euler's method is to find the value of the dependent variable y at discrete points. Okay, instead of coming up with a continuous function. So what we can do is, okay, let's say we know at the value of x equals to 0, we know the initial value y naught. Okay, then what we will do is what we'll do is we will say that, okay, this bivariate function fxy denotes our slope, okay, dy by dx or ddx of y we call it, and we also know the initial values at x naught and y naught, and we know the corresponding functional value at x naught and y naught. Okay, so which means that we know the slope at that particular initial point. So given this information, our goal is to find the value of y at other discrete points. Okay, and by other discrete points we mean that the other discrete points are some steps ahead of our initial point, and that particular magnitude of that step is determined by us. Okay, when we decide on the step size, basically, which is denoted using h. So let's see what's the main gist behind the Euler's method. Let's go back to our memo paper. Okay, let's go to the next page. Okay, so suppose I have a graph that looks something like this, and let's draw the graph. So initially we don't know how the graph looks. Okay, so for illustration purposes, I'm drawing a simple graph, but in reality we don't know what the graph looks like. Okay, we'll try to approximate the behavior of the graph basically. So let's say the curve looks something like this. Okay, so we already know two things, right? We know that our slope dy by dx is a bivariate function f of x comma y, right? And we also know the say the dependent variables value at x naught, okay, which is y naught. Let's denote it as y naught. So let's say we have a starting point x naught, which is somewhere over here. Okay, so let's project it upwards. Very bad projection. Let's say something like this, right? So this value over here, we know the value of y at that particular point, right? Let's call it y naught, right? Fine, y naught. So what we can do is, okay, we know the value of y at this particular point, and we also know the equation of the slope, right? We know that if x comma y is the equation bivariate function that dictates the behavior of the slope, right? So let's draw the slope over here because we know the value of the slope. Say f of x naught comma y naught, what will it give me? It will give me the slope at this point, right? And this is the point x naught comma y naught, and the slope at this point, or the gradient at this point, is something like this, right? Let's draw a straight line, roughly something like this. So I'm basically eyeballing it, something like this, right? Okay, so okay, I know the slope of the straight line that passes through this point over here, that tangentially touches the curve. So what we can do is, okay, now I'll proceed by a particular step. Okay, so I will go ahead or to the right side by a particular step. Let's call it h. So we denote step size using h, right? So let's say I'm going to x. Let's use a different color. So let's say I'm going to x1, where x1 is h units in front of x0. Okay, we call it the step size. So okay, since now we know the value of x1, because x1 is basically x0 plus h, we'll project it upwards, and we'll say, okay, the value of the straight line slope, of the slope that we got, the value of that straight line at this particular point x is my approximated value of y1. Okay, so why do we call it the approximate value of y1? Because we know for sure that our actual exact value is somewhere over here, right? Our y1 should be somewhere over here. So we call this what, the functional value, the dependent variable's value at the point x1. This is the actual value, right? And what we got here is more of a predicted value. So we denote it as y1, and this is our predicted value. Fine. So now that we know the actual value and the predicted value, we can see a disparity between them. Okay. So we'll talk about this disparity. We know the disparity is dubbed as error, right? So this is called the local truncation error. We'll talk about that in a bit, okay, in the upcoming segment of the lecture. So let's focus on the Euler's method right now. Let's try to derive the formula at first. So okay, now that we saw how we can approximate the value of y at a particular point x1, which is h units ahead of our initial point, we can iteratively perform these same two steps, right? So what we can do is, at this point, I know the I know the value of my bivariate function, which is f of x1 comma y1, right? So whatever value this function will give me after plugging in the value of x1 and y1, because I know the value of x1 and y1 now, right? So it will give me a different slope, right? So it should look something like, say, this. So I'm very bad at drawing straight lines using the mouse. Something like, say, this. Fine. So what what's happening here is that, okay, so this pink color slope that I have ended up with, this straight line will help me approximate the value of, say, another point ahead of x1. Let's call it x2. Okay, so let's say x2 is somewhere over here, roughly the same step size, and I'll be able to calculate the value of y2 for the point x2, right? Whereas the actual value of y at the point x2 is somewhere over here. This is the actual value, this is the predicted value, right? Fine. So we can go on ad infinitum until we reach our right hand side or the upper bound, right? Fine. So that's how basically the Euler method works. Okay, so that's how it can approximate the value of y at certain discrete points when you go ahead step by step, where you set the magnitude of the step size beforehand. Okay, you set the value of h beforehand. So let's see how we can do it, how we can come up with a formula for it. Okay, So let's erase this over here. Okay, so let's say okay my let's try to draw a little bit more over here for better visualization. So let's draw a straight line here. So this disparity over here is of course x1 minus x0, right? This distance over here and this distance over here. So this, let's call it the perpendicular distance, is what? Y1, the predicted value of y1 minus the initial value y0 that we already knew, right? So okay, we can say that this blue colored line, the slope of this line, let's call it m, is equal to what? Delta. We know that the slopes formula is delta y by delta x, right? The difference between the ordinate values and the difference divided by difference between the abscissa values, right, or the x values. So we can write it as something like what? Y1 minus y0, y1 minus y0 divided by what? X1 minus x0, right? Fine. So now that we know the formula for the slope, we can say okay, I have already defined my slope as a bivariate function, right? So we know that our bivariate function looks something like what? F of x comma y, right? But to be more precise, the slope, this blue colored line over here, is the slope at the point what? X0 comma y0, right? This at this coordinate, right? So we can plug in those values. You can say okay, the functional value of the bivariate function's functional value at x0 and y0 is my slope at that point, or which basically denotes that blue line over here, right? So this value is equals to what? Y1 minus y0 divided by x1 minus x0. Okay, fine. So now that we know this, now some simple algebra will help us come up with the formula. So let's take this whole numerator to the left hand side like this, and let's perform some, okay, let's take this denominator to the top, so we get something like this, right? X0 comma y0 times x1 minus x0. Okay, fine. So okay, so we have already said that the difference between the consecutive x values is the step size, right? So we can replace x1 minus x0 using the step size, and what more we can do is we can take this y0 to the right hand side, right? Then this minus will become plus. So we can say okay, y1 is equals to y0 plus f of x0 comma y0 times h, right? Fine. So this is, long story short, the formula that you use in terms of Euler's method, the formula that we use to approximate the value of y1 given our y0 point and our bivariate function that dictates the behavior of the slope, right? And a particular step size that we have set beforehand. So to make it more general, to generalize it, let's write something like what? So in order to find the y value at the I plus 1 step, so y sub I plus 1, we take the value of y at the ith step plus, so this is of course a subscript, be a bit smaller, at the ith step plus the functional value of the bivariate function of the slope at the ith step. So we call it what? F of xi comma yi, right? Times h. So this thing over here is the iterative formula for the Euler's method. Okay. So if you know the value of y at a of the dependent variable y at a particular point y1 y sub I is the dependent variable, and this is what? This is the slope at that point. So this is the slope. So we know the value of dependent variable at a particular point yi. We know the slope at that point, and we also set a step size beforehand. Okay, so this is the step size that you use to progress step by step. Okay, so if you know all these three things beforehand, what you can do is you can come up with an approximation for the value of the dependent variable y at the succeeding step or the next step, right? Fine. So this is the approximation y sub I plus 1. We denote it using y sub I plus 1. Fine. So y sub I plus 1 equals yi plus f of xi comma yi times h. Fine. Now that we know how the formula came about, let's see if we can try to derive it using any other approach. Okay. Okay, we are back to the slide. So these two slides over here basically discuss the derivation approach, the thing that I have shown in our bamboo paper just now. So if you look at this GIF over here, you'll be able to see. So I drew only two steps, right? X naught, x1, and x2. So you can see how the approximation of the how the approximation progresses iteratively, right? So for the initial point we approximate the next point, and we using this point we approximate the next point, using this point again we approximate the next point, and so on. Okay, so what you can see are two observations, right? So we are not perfectly approximating the points, right? And the errors that we are accumulating at each step are having a compound effect, right? They are basically having a domino effect, so they are getting accumulated and increasing rapidly, right? So at the first point we are seeing a perfect uh, coincidence with the actual curve. For the second point we are seeing a slight deviation. For the third point we are seeing a bit more deviation, and the deviation continues to increase, right? So we'll discuss about this error in a bit, but firstly let's see how we can derive the same formula that we have just derived, this one over here, using the first two terms of the Taylor series. Okay, so the idea is very simple. Just follow along. Okay. Okay, we are back to our bamboo paper. So let's go to the next page. So if you recall, our Taylor series looks something like this, right? So we have f of x plus h equals what? So we, for the functional value at any other particular point, we needed the actual functional value at the actual point x. Then we said that okay, we needed every other derivatives, right, at that particular point x. So f prime x times h, where h is the step size, plus f double prime x plus divided by 2 factorial times h square, right? If you recall, it looks something like this, and then f triple prime x. So basically all other higher order derivatives. So this thing will be 3 times h cube and so on, right? Fine. So in order to draw a parallel between the Euler's method formula and this Taylor series over here, let's try to do some. Let's try to see how we can do that. Okay. So let's say okay, the functional value at the point x plus h. Let's denote it using yi plus 1. Okay. So our the value of a dependent variable at the I plus 1 step will be h step ahead of our uh, functional value of the dependent variable's value at the ith step, right? So yi plus 1 will be h steps ahead of yi, right? So using leveraging that intuition, we are writing okay, f of x plus h, the functional value at x plus h point will be, let's call it yi plus 1. Okay, then what do we call the functional value at x? We call that yi, right? Fine. And we say okay, since f prime x is this, so we're using f prime x, the first order derivative over here. So we say okay, let's denote it using something like this, dy by dx, and the value is at, of course, xi comma yi, right? Fine. So and we multiply it using h. So this whole thing becomes this, because we know the derivative is calculated at the known point xi yy, right? Yi. And by derivative we mean the slope, right? We have to know the slope at that particular point. Then let's proceed and let's say okay, f double prime x will look something like what, d square x by dy square, oh sorry, d square y by dx square, times what, so times, this is the value at, slope is at by the uh, second order derivative at the point xi comma yi times 1 divided by 2 factorial. So this 2 factorial will persist over here, and we have the h square, right? H square. So I'm skipping the cubic term, so it will basically uh, progress as something like this. Okay, so what we can do is, okay, so instead of writing h, we know that the value of h in this case is what? The difference between consecutive x values, right? Or the consecutive difference between the consecutive independent variable values, and in this case our independent variable is x, right? So we can rewrite it as something like yi plus dy dx at the point xi comma yi, and we can say, okay, this is xi plus 1, so the point that is ahead minus the point that is behind, or the succeeding point minus the preceding point, plus d square y divided by dx square at the point xi comma yi times 1 divided by 2 factorial. This 2 factorial will come over here, and instead of h we are writing what? Xi plus 1, xi plus 1 minus xi, the succeeding point minus the preceding point whole square, right? And the cubic term will be same. I'm just keeping it for the sake of brevity. Okay, fine. So now that we know how to basically dub the whole thing using the Taylor's theorem, using the Taylor series, what we'll do right now is, okay, we'll say, okay, let's consider the first two terms of the Taylor series. Okay, so we say we consider the first two terms. So let's see what happens. So when we do that, we end up with something like yi plus 1 equals yi plus, so we know that our slope, the value of our slope is dictated by the bivariate function, right? F of x comma y, right? And we know the slope is calculated at this particular point xi comma y, right? So we say, okay, the value of our bivariate function at this point xi comma yi is equal to the slope at that point, right? So we can replace it using f of xi comma yi, and the rest will remain as it is. Okay, xi plus 1 minus xi. Fine. And for the second case, there is no second case since we are considering the first two terms. So we end up with this thing over here, right? Now, if you notice carefully, what you can see is, okay, we have ended up right back where we started, in the right back where we ended up the last time, which is what? Y of I plus 1. Our approximation at the point at the I plus 1 step, the approximation of our dependent variable y is equal to what? Y sub I plus h times f of xi. So let's, instead of writing h now, let's sake of for the sake of consistency, let's write it as something like this: xi comma yi times h, right? Because this thing can be replaced by h. So what we have ended up with is the same formula, right? The same formula for the Euler's method that we have derived just a while ago, right? So let's go back to our previous page. So this one, right? Yi plus 1 equals yi plus f of xi yi times h. And we have ended up with the same formula here just by considering the first two terms of the Taylor series. Okay. So if you notice that when we consider the first two terms of the Taylor series, we're leaving out an infinite number of terms, right? From the third term and so on, right? So this whole thing will be our truncation error. Okay. So let me write it a bit clearly. Truncation error. Okay, so how do we quantify this truncation error, or how do we set the say upper bound for it in order to say express it using the BGO notation? So let's go back to the slide and discuss it. Okay, so we won't dive into the nitty-gritty details or the maths behind the bounding of this truncation error, because we have already learned this in our uh, third lecture, right? In our Taylor's theorem lecture, right? How to use the remainder theorem to come up with the bounds for the errors, right? So we'll just see how the truncation error, the local and the global truncation error looks like. Okay, let's go back to our presentation. Okay, so now that we are back, Okay, so this slide basically discusses what I have just shown you in the bamboo paper, the same derivation. You can go through it if you want. Okay, fine. So how do the truncation error manifests itself in Euler's method? Okay, so the Euler's method, as you can see, is not a perfect method of approximation by any stretch of the imagination. So it accumulates a lot of error. Okay, so there are basically two types of error, two types of truncation error to be more precise, that it accumulates at each step, or combinedly. Okay, so the two sources of errors are the error that we face while approximating the integral curve by the tangent line or the slope line. Okay, so we just know about the two sources of error from now. I'll try to make you visualize this in the bamboo paper in the bamboo paper in just a bit. Okay, and the second type of second source of error is the accumulated error. Okay, so since at each step we are calculating the approximation using a faulty previous approximation, which means that the approximation that we end up at the ith step yi is not a perfect approximation, right? It has some errors associated with it. That means when you use that yi in order to compute the value of yi plus 1, it will mean that that error will propagate step by step, right? So it will also propagate to the I plus 1 steps approximation, right? This is basically just like a domino effect or a compound effect. Okay, it basically compounds and together forms a very big global truncation error. Okay, so for the first source of error, we call it the in the case of the first source of error, we call it the local truncation error, which is basically the difference between the approximation and the actual value at the ith step. And the global truncation error is the effect of all the local truncation errors that we basically encounter at each step. Okay, their whole compound effect together, the cumulative effect together, is called the global truncation error. Okay, so let's go back to our demo paper and try to see how they look like. So okay, let's go back to the previous figure that we just drew a while ago. So yeah, so see when we knew the initial point and we knew the slope at that point, right? So using these information, we calculated the x1, the y1 value, right? Or the value of the dependent variable at the point x1, right? So this y1 we predicted at somewhere over here. But the actual value was colored in purple, right? It was somewhere over here, the actual curve. We don't know what the curve looks like, but for illustration purposes, I drew the curve, and the curve says that okay, the actual value lies somewhere over here. And this disparity over here, we call it the local truncation error. Okay, let's try to label it. So this thing over here is the local truncation error. Okay, at the point step I. So since for the I over here is 1, oh sorry, the yi over here is 0, right? So we are calculating yi plus 1 as some y1. So et0 is this thing over here. And see, now that we use this faulty or inaccurate y1 in order to compute the value of y2, we are actually propagating this error to the next step, right? So the effect of this inaccuracy or the effect of this error et naught over here will propagate to the next step when we calculate the value of y2, right? So this thing over here is our truncation error, local truncation error yt1. The combined effect and the effect of yt naught is inherent in the effect of yt1, right? So we call this the accumulation of all these errors. So at each iteration, we call it the global truncation error. Okay. So now I think the concept is pretty clear up to now. So let's go back to our slide and see how we can set bounds for it. Okay. All right, so our local truncation error is the rest of the Taylor series terms, right, that we have just shown a while ago in the bamboo paper. So this thing over here, we can approximate it using our remainder theorem, right? And so if you click on this link over here, you will get the whole mathematical derivation behind these bounds over here. These are not in your syllabus, which is why I did not include them in the slide. But if you're interested, you can click this link and check it out. Okay, the complexity analysis of the truncation error. So long story short, what happens is that local truncation error is directly proportional to the big O of h square, okay, an order of h square, and the global truncation error is proportional to big O of h. Now you might think, why is the local truncation error order of higher degree compared to the global truncation error? Okay, it only makes sense that the global truncation error will be higher, right? Because it is accumulating the local truncation error at each step, right? So what happens is that in general, when we use the step size, we use an infinitesimally small value. Okay, the value generally resides between 0 and 1. And I think you guys know that within the bounds 0 and 1, the curve of h square is below the curve of h, right? So the value, the square of a decimal of a value of a continuous or a decimal value less than 1 and greater than 0 is smaller than itself, right? So you can check it out if you want. So in Desmos, the curve looks something like this. Okay, the red curve is the h square curve, and the straight line, the blue line is the h line. Okay, the big of h is straight line. Fine. So this is one intuition to basically justify the big O of this local truncation and the global truncation errors. And another thing is that okay, the when you apply the mean value theorem on the geometric series formula on this part of the Taylor series over here, we'll end up with these bounds. Okay, so as I've said before, you can click on the link to basically know about the whole derivation if you're interested in the math behind that whole bounds. Okay, the bounds. Fine. So these local truncation error, which are in the order of big O of h square, they gradually accumulate to form global truncation error of big O of h. Okay, fine. So now that we know how the local and the global truncation goes with respect to the step size, proceed and see. Let's proceed and try to solve an example. Okay. So the example is that okay, we have a ball at a particular temperature 1200 Kelvin, and we are cooling it down at room temperature, okay, at ambient temperature of 300 kelvins. Fine. So the ball was heated up and now it's cooling down in room temperature, and the the first order differential equation or the ordinary differential equation that dictates the change of the temperature with respect to time looks something like this. Okay, d theta d dt of theta equals minus 2.2067 times 10 to the power minus 12 times theta to the power 4 minus 81 times 10 to the power 8. Okay, and we are also given the initial value of the temperature, which is theta 0, which means the time and the value of the temperature theta at time t is equals to 0 seconds is 1200 Kelvin, right? Because the ball was initially 1200 Kelvins hot, right? It was very heated. Fine. So the units are given over here, and we are asked to find the temperature at t is equals to 480 seconds. Okay, and we have to use the Euler's method to do that. And we they said that we can use a step size of h equals 240 seconds. Okay, so every time we can proceed or go ahead by 240 seconds, we can increase the value of t by 240 seconds. Fine. So let's see how we can approximate the value at this value of the temperature at this time over here, and we will try to compare with the exact value and see how accurate our assumption is or how accurate our approximation is. Okay, fine. So we know our ODE or our first order ordinary differential equation. We know how to denote it using a bivariate function. So we'll just replace this whole thing using our bivariate function, and we are good to go. So we know our bivariate function now, and we also know the Euler's method formula that we have already derived using two approaches, right? So instead of using y, they are using the notation theta, and instead of using x, they are using the notation t. So theta stands for temperature and t stands for time in seconds, and theta is in kelvins. Fine. So the theta sub I plus 1 equals theta I plus f of ti comma theta I times h. Okay, so this is our Euler's method formula, and we'll just basically apply this formula. We'll plug in our values that we have using our calculator and try to come up with the theta 1 value. Okay, or the approximation of the temperature at the first step. Okay, by first step we mean when we go ahead by 240 seconds. Okay, if you recall, one step was 240 seconds long, right? So theta 1, which means after 240 seconds, the ball will approximately be 106.09 kelvins hot. Okay, the temperature of the ball will be 106.09 kelvins. So as they have said here, theta 1 is the approximate temperature at 240 seconds. Okay, so this is the approximation. Fine. So now we can go ahead by one more step, right? Because they have asked us to find the value at 480 seconds, and if we divide 480 by 240, we get 2, right? Which means we can go ahead by two steps. So step 1 is complete. So let's go to step 2. So in our step 2, our value of I is of course 1. We know our time t1 as 240, which we have calculated just here. T0 plus h is basically t1. And we know our theta 1 approximation to be 106.9, which we have calculated just here, right? Fine. So we'll use the same formula, Euler's method formula, and come up with theta 2, which is our final approximation at time t equals to 480 seconds, right? Which is, they have shown over here. So if you plug these values into your calculator, you will get something like 110.32 kelvins, right? So they say that okay, at time 480 seconds, the ball will be 110.32 kelvins hot. Okay, 32 kelvins in temperature, right? So this sounds a bit unintuitive, right? Because at time 240 seconds, the ball is cooler than the temperature at time t is equals to 480 seconds, right? Which is kind of physically impossible unless you are supplying external heat source to the ball, right? So we can say with a good degree of certainty that the approximations that we are getting are not that accurate, right? So let's try to get a reality check on that. So if you so the question that they have posed, this differential equation over here, this for our differential equation over here is the solution to that is basically the solution to this non-linear equation. Okay, so this if you apply any root finding algorithm and find out the root of this non-linear equation, you'll get theta exact to be 647.57 kelvins at t is equals to 480 seconds. Okay, so see how far apart our approximation and our exact value is. So as I've said before, the Euler's method is a very imperfect method. Uh, so use it at your own discretion. Okay, fine. So let's try to visualize the graph. So if you plot this nonlinear equation, you'll get the exact solution to be something like this. And what we have seen is that our approximation with step size 240 seconds looks something like this, right? So for the first step, we get something like this. So temperature at a value something like this, and for the second step, we are getting something like this, right? So the value is actually increasing. Fine. So if we use just like we have seen before, if we use step size h equals to 240, we end up with 110.32, right, which is somewhere over here, right, a little below 200, right? So if we use various step sizes, for example, if we use only a single step of 480 size, we'll end up with a very bad approximation of minus 987.81 kelvins. We'll get to see the graph in a bit. Just notice this table over here for the time being. Okay, so as we decrease the value of our step size, we are getting lesser and lesser value of errors, right? So this over here is our global truncation error. Okay, so if you recall, our global truncation error looks something like this, right? It was order of what, big O of h, right? Which means we can say that okay, if we decrease our step size by half, we should expect what, decrease of our truncation, global truncation error by half as well, right? And similarly, if we decrease our step size by half, we can expect what, one-fourth decrease, or a decrease to one-fourth what, local truncation error, right? Which means our local truncation error will be one-fourth of what it used to be. Okay, so if we just set the step size to be one half, fine, since the square of one half is 4, pretty easy, right? Fine. So okay, so if you look at these values over here for very high step sizes, we are not getting a decrease by half, right? We are getting much more than that. So 1635 is reducing down to 537, right? A very drastic decrease. But if you look at the smaller step sizes, for example from 60 to 30, we are noticing a decrease by half, right? So from 32 it decreased to 14, which is roughly half of 32, right? Not exactly half, roughly half. Okay, if we go to lower and lower step sizes, let's say infinitesimally small step sizes, we'll be able to notice the big O of h square and the big O of h bounds. Okay, very saliently. Fine. So now that we know the trend of the global truncation error with respect to the step size, let's try to visualize it in a graph. So the exact solution, just like before, is this nonlinear equation over here. So when we use step size of a huge step size of 480, we end up with an approximation somewhere over here, right? Because the slope at this point is something like this straight line over here, and we end up with this approximation, which is very far apart from our actual value, right? So this whole thing is our error. We end up with a negative temperature value, right? Which is of course very asinine, uh, very asinine approximation, right? Fine. So when we use the step size h equals to 240, the thing that we did in our example over here. So when we use h equals to 240, we end up with an approximation somewhere over here, right? A little above 100, which is 110 point something, right? 110.32. So this is also very bad approximation. So when we use, so we need to decrease the step size by half. If we use a step size of 120, we get somewhat close to the exact value, right? So our exact value for h equals to 120, we get what? 546.77. If you recall, our exact value was 647.57. So 546.77 is very near to 647.57, right? Now the trend is that, okay, if we keep decreasing it by half gradually, we'll end up converging to the exact solution. Okay, so if you want to use Euler's method, you have to come up with you have to use basically small step sizes in order to get good approximations. Okay, so this graph basically portrays the effect of the step size in Euler's method. So the more the step size we use, for example, when we use 480 step size, we end up with a very bad approximation of minus something, right? Minus 987 point something, which is impossible for this problem, right? Fine. So when we use step size of 240, we get a approximation of what, around 110.32, and gradually if we decrease, we end up with something very close to the actual value, which is 647.57, right? Something over here. So if we keep decreasing and decreasing, infinitesimally small, and we end up with, it converts to the actual exact value, right? Fine. So that's how an application of the Euler's method can be done for a common physics problem. Okay, fine. Fine. So the thermodynamics problem to be more precise. Fine. So okay. So now that we know how to apply the Euler's method to a particular problem, uh, we'll try to talk about uh, one of its more important applications, okay, which is we can use the Euler's method to approximate the value of a definite integral. Okay, so let's go back. So for this, we need to basically recapitulate our uh, fundamental theorems of calculus that we learned in first year, back in first year. Okay, I think you guys already forgot it. We'll try to recall that a bit. Okay, let's go to bamboo paper and see what these theorems try to say. Okay, now we are back to our bamboo paper. Let's go to the next page. Mm, okay, so suppose we have a graph function that looks something like this. Let's say roughly something like this. So let's call this graph f of x. Okay, so this is a function f of x, and it is continuous and real valued within a closed interval. Let's say this is the closed interval within which it is continuous and real valued, and the lower limit of the interval is a, and the upper limit of the interval is b. Okay, so now that we know the lower limits and the upper limits, we can say, okay, what does the first fundamental theorem dictate? So it says that, okay, if we take a particular value of x, so instead of, to avoid confusion, let's denote it using t. Okay, so let's denote it using t. So let's say this is ft, which means this, along the y-axis we have ft values, and along the x-axis we have t values. Okay, fine. So for a particular point, arbitrary point x within the closed interval a and b, within the closed interval, which is the lower limit a and the upper limit b, if we take an arbitrary point x, which means x is an element of what is within A and B, right? Fine. If we take this point X and say, okay, let's calculate let's project it upwards. If we calculate the area under the curve within this sub interval, so we know that area under the curve is denoted using what? The summation or the integration, right? In the continuous case, we call it the integration. So this thing over here is the summation from the lower limit a to the upper limit x for the function f of t with respect to dt, right? So we say that okay, let's use another function. Let's call it capital. Let's call it capital F. We call it okay. The value of capital F of x, which means the value of capital A of x, f of x will be the uh, whole value of the area that has been shaded in purple, basically. Okay, so the area that is under the curve between the lower limit a and the upper limit x. So this upper limit x is purely arbitrary. The area underneath the curve, the integration of the definite integral value is equal to another function, capital F of x. Okay, if we try to draw the graph of capital F of x, let's say this is x, and this is capital F of x. Okay, fine. So for this particular, so we have a lower limit a, of course, and we have an upper limit b, of course, for the value of x. And between these two ends of the interval, we are taking an arbitrary value of x, right? So this x is different this x, obviously. Fine. So for this x, we end up with a particular set value of f of x, right? So this thing over here is this over here. Okay, fine. So let me try to use a different color in order to mark it. Fine. So mm, this thing over here corresponds to this point over here. Okay, fine. So if you eyeball the area under the curve from 0 to say infinity, we should get what? So the area is gradually increasing, right, underneath the curve. Let's try to draw the curve. The curve should look something like, say, like this. So initially it's a non-zero area, 0. So let's say it looks something like this, right? So as we go towards the right, it will keep increasing. So this is not an exact graph of the capital F of x, just an approximation. Okay, fine. So let's try to draw it a bit more. I think this will suffice. No worries. Fine. So okay, okay, so the graph of capital F of x that we have ended up over here, we say that this capital F of x function is differentiable within the lower limit a and the upper limit b. So within this, between these two ends of the interval, this function capital F of x is continuous and differentiable at every single point. Okay, so we are considering what the open interval. Okay, so a and b are not included, obviously. So from values greater than a and from within values less than b. Okay, so we say that okay, the the first derivative or the differentiation of capital, this is the first fundamental theorem. Okay, the capital f of x's first differentiation of the capital F of x function is our original function small f of x. Okay, so since the derivative of this the first derivative of this capital F of function capital F of x function yields our original function small f of x, we call this capital F of x as our antiderivative. Okay, antiderivative. Fine. And this is our original function, okay, which was the actual integrand that we're trying to integrate, right? And this capital F of x is our antiderivative at the point x. Fine. So this is what basically the whole first fundamental theorem tries to imply. So this thing is valid, of course, for values of x, which are within the which are arbitrary and fall within the open interval a and B. Okay, A and B are not included. Yes, not non-inclusive interval from A to B. Okay, fine. So this is our first fundamental theorem. Fine. Now let's try to talk about the second fundamental theorem. So let's try to change the colors of it. Okay, so notice that our antiderivative function's value at a is what? Capital F of a, right? Capital F of a, and the antiderivative function's capital F of x, its value at b, or the upper limit or the right hand limit, is what? F of capital F of b, right? So we say that okay, the area underneath the curve f of t from the lower limit a to the upper limit b. So this whole thing over here, this thing is basically the difference between this whole difference. Okay, the difference between the, so we say that okay, the integration of f of x with respect to dx is equals to f of b minus f of a. Okay, so this functional, the antiderivative value at the point the upper limit minus the antiderivative value at the lower limit is the value of the area underneath the actual curve. Okay, so f of b of course resembles what? This whole area, right? So this whole area, right, from p to minus infinity, right? Okay, and the value of the function, the value of what? The uh, capital A f of a, which is the antiderivative functional values, antiderivative functions, functional value at a is what? This whole area, right? So if we subtract this two, if we subtract f of b from f of a, we get this area in the middle, right? Which is the area underneath the curve, which is what we are aiming for, right? In order to find the integral value of the actual function. So this is the second, we call it the second fundamental uh, theorem of calculus. Okay, fine. So let's see how we can use these two theorems in order to apply the Euler's method to come up with an approximation for a definite integral. Okay, let's go back to our presentation. Okay, now that we are back to the slide, so you can go through these formal statements of these two theorems. So these are pretty self-explanatory, and you can look at this graph over here in order to visualize how the antiderivative is working. Okay, so since they have capped off the area at the y-axis, they are starting from the origin, right, for the value of capital F of x, and as we increase the area, the value of the antiderivative also increases, and in order to find out the area underneath the curve, which is the capital S minus the small s, therefore basically invoking the second fundamental theorem of calculus, which is this one over here, in order to find the difference f of b minus f of a, and they ultimately consequently find the area underneath the curve between the specific interval, right? Fine. So you can click on this link if you want to visualize the GIF. Fine. Let's proceed. So how do we use or utilize the Euler's method in order to in order to approximate the value of a definite integral? Okay. So so instead of looking at the slides, why not go back to our bamboo paper and do it by hand? Okay. Okay. Now that we are back, let's go. Okay, so let's say we want to find the value of an integrand I, which is defined as the integration of a particular function f of x with respect to dx from the lower limit a to the upper limit b. Okay, so we write it a bit more clearly. Fine. Okay, so how do we use the Euler's method to basically find out this, right? So recall that since we have said okay, the Euler's method is used for coming up with approximations of the solutions to first order ODEs, right? First order ordinary differential equations. So why not express this integral in that form? Okay, so we know that for our Euler's method, we write our slope as something like this, right? Dy by dx equals to a particular function, right? So we use a bivariate function in order to uh, denote our slope, right? But for this integral case, just wait and see how we can invoke the bivariate function a bit later. Okay. So initially, what we'll do is okay, we'll take this we'll take this, what we call it, the integrand, right? They take this integrand and express it as the differentiation of a particular variable y. Okay, so if you look carefully, this y is the same thing as the integrand I, right? Because we know the differentiation of an integrand is the actual function, right? So in this case, di by dx will give me f of x, right? So this is the same thing. Y here is the same thing as, uh, we can write it as something like this. So this y here is equal to the actual integrand I. Fine. So now that we have basically cast the actual integrand as something like this, we'll take another thing that we need for the Euler's method, which is what? An initial condition, right? Or an initial value. So say that, see that we have a lower limit a, right? Okay, we say that the integrand at the lower limit a, or the value of the dependent variable y at the lower limit a is equals to 0. Okay, we suppose this, we take this as an initial presumption, okay, in order to initiate our Euler's method. So we take this and let's see how. Okay, so now in order to find out the value of the integral, we try to find the value of the dependent variable y at the upper limit b. Okay, so that's a discrete point, right? So we know we can utilize the Euler's method to calculate the value of the dependent variable y at this discrete point, right? So our target is to find the value of y of b, right? So in, if you find the value of y of b, essentially we will end up with the value of the integral, okay, an approximation of the value of the integral. So let's go back to our slide and see what we can do. So this thing over here, of course, instead of question mark, what we'll end up with is the integral that we are looking for, okay, f of x. Fine, let's go back to the slide. Okay, now that we are back, let's see precisely where did we invoke the first and second. So we use the first fundamental theorem, or the theory behind the first fundamental theorem, for the first assumption. Okay, for the first assumption. So what we did was we said that, okay, ddx of y was equals to our the integrand function, right? The function that we are working with inside the integration sign. So recall that for the first fundamental theorem of calculus, we said that the differentiation of the first order, the differentiation of the antiderivative will give us our original function f of x, right? So since we know the antiderivative of the integral to be y, we use the notation I or y, right? Conventionally we use I. In the case of Euler's method, we use y, okay? So dy by dx will give me what? The original function f of x, okay? So this is our initial assumption that we where we utilize the first fundamental theorem to come up with, okay? And for the first and for the initial condition y of a equals 0, which means the value of the dependent variable y at the point the lower limit a equals to 0. For that, we that's our presumption. Okay, so we are saying, okay, the value of the area at that point, or the value of the antiderivative function at that point is 0. Okay, so what we can do is, okay, in order to find the value of the integral, we try to find the value of y b. Okay, so the value of the dependent variable y at the point b, which is somewhere over here. So okay, so if you recall, the second fundamental theorem of calculus says that, okay, if I subtract the antiderivatives value at the point b, uh, if we subtract the antiderivatives value at the point a from the value at the point b, we end up with the integral value of the function, right, from the lower limit a to the upper limit b. So since we took our antiderivatives value at the lower limit to be 0, so we don't need to perform yb minus ya, right? So when we end up eventually finding yb, that's our final answer, okay? So we don't need to subtract ya from it, because subtracting ya is redundant, right? Because we are subtracting 0 from the actual value of yb. So whatever value of yb that we find, that will be our final answer that we're looking for, the value of the integral, okay, according to the second fundamental theorem. Right. Now let's try to apply this technique, this application. We'll try to see how this application of the Euler's method works on an example integration. Okay, on an example definite integration. So we are trying to integrate the function c6x cube from the lower limit 5 to the upper limit 8 with respect to dx. Okay, so we have to use the Euler's method, and we have to come up with an ODE in order to represent this integrand, right? So and they have asked us to use a step size of h equals to 1.5. Okay, so let's see how we can do that. So first order of things is to cast this integrand as a first order differential equation. Okay, so what we can do is, okay, we set dy by dx equals to 6x cube, right? Because we are integrating 6x cube over here, and we are taking our lower limit. The value of the lower limit is 5, right? We are taking the antiderivatives value, or the antiderivative function's value at the point 5 to be 0. Okay, that these two are our initial presumptions. Fine. So now that we know these two, we can apply the Euler's method. Okay, and we know our theory part tells us that when you find the antiderivatives value at the point 8, that will give us our final answer. So our target is to find the value of y 8. Okay, fine. So that we know the slope or the what we call it, the slope dy by dx is equals to 6x cube is also the bivariate function that we use in our Euler's method, right? So here is where the bivariate function comes into play, and the initial assumption is the same as before. So in our Euler's method formula, we saw that we derived that y sub I plus 1 equals to y sub I plus f of x sub I comma y sub I times h. Okay. So for step 1, so let's say 8 minus 5 is 3, right? And they have told us to use a step size of 1.5. So naturally we can say that, okay, we need to perform two steps of the Euler's method. Okay, because 1.5 plus 1.5 gives us 3, right? So when we go ahead by 2 steps, we'll end up at the upper limit, right? Okay, so let's do step 1 at first. For step 1, the value of I is 0, of course. We know the value of x0 to be 5 because we know our lower limit, and we also assume that the value at that point, the value of the dependent variable at that point is 0, right? Which means y0 is equals to 0. And our step size is given from the question, it's 1.5. We find the value of x1 to be 6.5. We plug, so we know the value of 6.1 now. Now we need to approximate the value of y1, right? So in order to come up with the approximation, let's apply the Euler's method formula. We say, okay, y1 equals to y0 plus f of x0 comma y0 times h. Okay, so if you plug these values into your calculator, you should get a value 1125. We say that, okay, this is an approximation of my antiderivatives value at the point 6.5. Okay, because our x1 value is 6.5. Now let's proceed to the next iteration of the step 2. Let's proceed to step 2. In step 2, our value of I will get increased by 1, of course. Now our x1 that we have garnered from our last step in our preceding step was 6.5, right? So our x1 is 6.5, and we have done similarly for the y1. We have approximated that our value of y1 was 1125. So now we can similarly calculate the value of x2, which is 8, because we just basically added 1.5 to the x1, and our approximation of y2, similarly we end up with 3596.625. Okay, we say that this value is our approximation of the antiderivative function at the point 8. Okay, when x is equals to 8. So now that we have found our approximation for the antiderivative function at the point 8, 8 was our upper limit, right? If you recall, we needed to find the integral from 5 to 8, right? So since we have found this approximation at the point 8, we can say that whatever answer we have found, 3596.625, that is our final answer. Okay, that is our approximation of the definite integral. So we can say, okay, the integration of 6x cubed with respect to dx from the lower limit 5 to the upper limit 8 is the antiderivative value at the point 8 minus the antiderivative value at the point 5. And we have assumed this antiderivative value to be 0, right, as our initial presumption. So this is basically the same as subtracting our final assumption with, we are subtracting 0 from our final assumption, right? Which means our final assumption was the correct, was our final answer, right? So what we end up with is the integration of this value is something like 3596.625. And now in order to get a sanity check on this approximation, what you can do is you can analytically try to find out the these definite integrals value. So I have done that in my copy, and what we end up with is something like, the exact value is something like what 5200 me write it a bit more clearly. 5206.5. Okay, so what we can infer is that whatever approximation that we have ended up with is a very bad approximation, right? That's the disadvantage of Euler's method. It will give you very bad approximations when you take the step size to be too large. Okay, when you take infinitesimally small step sizes or reasonably small step sizes, you'll get good approximations. Otherwise, you'll end up with approximations that becomes what, that basically overshoots the actual value. Okay, the approximation is uh, very very widely deviated or f- very far from the actual exact value. Okay, the approximated value is very far from the actual value, as can be as exhibit as this example is an exhibit A of that case. As you can see from here, the approximation of a actual value of 5000 something is 3500 something, right? Very far apart, right? Okay, so now that we know how to apply the Euler's method for a definite integral, for approximating the value of a definite integral, and ended, we have come to the end of this lecture. So if you have any questions regarding this lecture, you know how to contact me, or you can, of course, write write any questions that you have in the comment sections. Okay, under the post that I will create while uploading these materials for this lecture. Okay, fine. So that's it from my side. Assalamu alaikum warahmatullahi wabarakatuh.